Look at any object near you, a coffee cup, a pen, a speck of dust. If you move it from one side of your desk to the other, you are certain of one thing: it occupied a specific set of coordinates at every moment in between. You believe in the trajectory. You believe that for an object to get from A to B, it must be somewhere in the middle. This is the tyranny of the line. It is a comforting fiction your brain tells you to keep you from losing your mind. In our daily lives, the path is the fundamental unit of reality. We build our entire understanding of cause and effect on the idea that things move through space in a continuous, logical sequence. If a car drives from London to Paris, it doesn't vanish and reappear in the ocean, it follows the road. This intuition is so deeply baked into your consciousness that you don't even think to question it. You see a ball in the air and your brain automatically draws a smooth arc, a parabola predicting exactly where it was and where it will be. But this arc is a lie. When Richard Feynman looked at the double slit experiment, he didn't see a particle or a wave. He saw the death of the trajectory. In the classical world, if you have two holes, the particle goes through hole 1 or hole 2. Your intuition demands this, or it demands a choice. You want the particle to have a history, a single, verifiable story of how it got to the detector. Physics does not care about your demand for a story. When we observe the interference pattern on the screen, we are seeing the wreckage of the concept of somewhere. If the electron truly followed a path, a single, thin line through space, it would have no way of knowing that the other slit existed. It would simply pass through its chosen opening and hit the wall like a tiny, predictable bullet. But it doesn't. The pattern proves that the electron's arrival at the screen is influenced by both slits simultaneously. This forces a sickening conclusion. The electron did not take a path, because if it had taken a path, it would have been in one place. And if it were in one place, the other slit would be irrelevant. We like to say the electron is delocalized, a sterile, academic word used to soften the blow. What it actually means is that the very idea of an object having a location while in transit is an illusion. There is no line, there is no middle. There is only the start and the end, and a terrifying silence in between where the path should be. You think you are moving through the world on a track. You aren't. You are just arriving at destinations, having somehow bypassed the necessity of the journey. So, if the electron isn't taking a single path, your brain immediately tries to bargain. You concede that maybe it takes two. You imagine the electron splitting like a cloud of mist, flowing through both slits at once, and then recombining. It's a messy image, but it's one you can live with. It preserves a sense of nearness. You assume that whatever is happening, it's at least confined to the area between the source and the screen. Feynman realized that this bargain is a delusion. If we add a third slit, the interference pattern changes. The electron is now aware of three possibilities. If we add 1,000 slits, the pattern shifts again. If we drill holes in the floor, the ceiling, and the walls of the laboratory, the math tells us that every single one of those openings affects the final arrival of the particle. The logic is relentless. If the particle is influenced by every available opening, then what happens when you remove the barrier entirely, when there is nothing but empty space between point A and point B? Your intuition tells you the particle takes the straight line. But Feynman's insight was that empty space is effectively a barrier with an infinite number of slits. If you don't track the particle, there is no reason, none at all, to assume it limits itself to the logical route. This is where the scale of the mystery begins to bloat. If 2 slits create interference and 3 slits create more, then the empty space between 2 points is actually a theater of infinite interference. The electron is not just going through the slits, it is probing the limits of the room. It is sampling the corners of the ceiling. It is feeling out the texture of the distant stars. You want to think of the double slit experiment as a localized anomaly, a weird quirk of subatomic physics happening in a small box. It isn't. The experiment is a leak, a tiny tear in the fabric of your perception that reveals how the entire universe operates. The 2 paths are just the beginning of a descent into a mathematical abyss where the number of possible routes ceases to be a number and becomes a continuous, suffocating flood of possibilities. We are no longer talking about a particle being in 2 places at once. We are talking about a particle being everywhere, at every time, in every conceivable way, simultaneously. You are looking at a single dot on a screen, but that dot is the final, condensed residue of a process that spanned the entire cosmos. The mystery of the two slits is just a polite way of introducing you to the fact that the universe does not believe in here. This brings us to the core of Feynman's disturbing discovery. It is called the path integral, but in the halls of physics, it is known as the sum over histories. Feynman proposed that to calculate the probability of a particle moving from point A to point B, you cannot just look at the straight line. You cannot even just look at the two slits. To get the right answer, the answer that matches reality, you must account for every possible path that connects those two points. And when Feynman said every, he was not using a metaphor. Imagine an electron emitted from a source. One path is the straight line, another path is a slight curve, but there are others. There is a path where the electron travels to the center of the sun, loops around a core of pressurized plasma, and returns to hit the screen. There is a path where it wanders to the edge of the observable universe, waits for 1 billion years, and then finds its way back to your laboratory a fraction of a second after it left. There are paths that move backward in time and paths that zigzag in shapes that defy the laws of geometry. Your intuition screams that this is absurd. You think the electron is too small, the energy is too low, the time is too short. You think these nonsense paths must be some mathematical trick, a placeholder for our ignorance. They are not. In Feynman's view, the electron does not choose a path. It does not prefer the short way. The electron literally, physically, explores the entire map of spacetime. It takes the long way. It takes the impossible way. It takes the way that involves colliding with a distant star and the way that involves sitting perfectly still for an eternity. The history of that single electron is not a single thread. It is a tangled, infinite web that covers everything that has ever happened or could ever happen. Every path is assigned a number of phases. Think of it like a little clock hand pointing in a certain direction. To find out where the electron will actually land, you must add up every single one of those clock hands from every single one of those infinite paths. This is the path integral. It suggests that the object we see is merely the sum total of an infinite number of ghosts doing infinite different things. You are not watching a particle move. You are watching a vast cosmic interference pattern of every possible history overlapping until only one result remains. You think you are a solid entity moving through a vacuum, but if Feynman is right, you are a collection of possibilities that have sampled the entire universe before you even took your next breath. If every possible path is taken, if the electron is truly visiting the center of the sun and the edges of the galaxy, then why does the world look so boring? Why don't we see electrons zigzagging wildly across the room? Why does a baseball thrown to first base follow a predictable, elegant arc instead of vanishing into a cloud of infinite histories? The answer is not that the crazy paths don't happen. The answer is that they cancel each other out. This is the chaos of cancellation. Remember the phases we mentioned, the little clock hands associated with every path. For the vast majority of paths the electron could take, the timing is a mess. One path's clock hand points up, another, only slightly different, points down. When you add them together, they sum to zero. They vanish. Imagine a stadium full of 1 million people, all shouting different, random sentences at the same time. From the outside, you hear nothing but a dull, meaningless hum. The individual stories, the histories, are still being told, but they are out of sync. They are incoherent. In the language of physics, this is destructive interference. The universe is essentially a graveyard of cancelled possibilities. Most of what happens in the quantum world is immediately erased by its own inconsistency. The path where the electron travels to Jupiter and back is real, but there are billions of nearly identical paths right next to it that are just slightly out of phase because they don't line up. They fight each other, they destruct, they ensure that the probability of you actually seeing an electron do something so ridiculous is effectively zero. This realization destroys our concept of laws. We grew up believing that the universe has laws of motion, rules that tell objects where they must go. Feynman suggests there are no rules, only an overwhelming overhead of noise. An object doesn't follow a straight line because it is told to. It follows a straight line because every other possible movement was so chaotic that it cancelled itself out of existence. Your reality is just the thin sliver of coincidence that survives this cosmic slaughter of histories. You feel safe because the world seems orderly. But that order is just the silence that remains when an infinite number of chaotic ghosts scream over one another until they all go quiet. If the world is a graveyard of cancelled possibilities, we have to ask, why does anything survive? Why does the straight line feel so solid? In the classical world, we call this the principle of least action. It is a grand, mathematical rule that says nature is lazy. It always takes the most efficient route, but Feynman's too deep look reveals that nature isn't lazy, nature is exhaustive. The straight line isn't a rule, it's a statistical accident. When you look at the path of a light beam or a falling stone, you are looking at the only place where the clocks happen to. A line. Think of a massive crowd in a plaza. Most are walking in random directions, their footsteps creating a chaotic, muffled roar. But in one specific corridor, a group begins to walk in perfect unison. Their footsteps land at the exact same time. Suddenly, you don't hear a hum, you hear a rhythmic, thunderous beat that drowns out everything else. This is what we call constructive interference. In the infinite sum of paths, there is one region where the phases don't fight. This region is the path of least action, the straight line. The paths that are almost straight have phases that are almost identical to the straight one, because they are in sync. They don't cancel out, they add up, they reinforce each other. They build a signal so loud and so strong that it becomes the only thing our coarse, human senses can perceive. We call this classical physics. But classical physics is just the name we give to the macroscopic shouting match that the straight line happened to win. This destroys the idea of a solid reality. You think you see a baseball flying through the air because it is a physical object following a physical law. In reality, you are seeing a massive, collective reinforcement of trillions of quantum histories that just happen to agree on one specific direction. The line you see is an illusion created by the overwhelming volume of the paths near it. It is a peak in a vast ocean of noise. If you were to shrink down, if you were to become as small as the electron, the agreement would break down. The surrounding noise would become just as loud as the signal. The straight line would dissolve into the fog of the infinite, and you would realize that the path was never there to begin with. The stationary world is a mask worn by a universe in total, frantic motion. If the particle truly samples the entire universe to move a single millimeter, then we have to abandon the most sacred concept in our perception of reality: locality. Locality is the intuitive belief that things are only influenced by their immediate surroundings. You believe that for something to affect you, it must touch you, or at least send a signal that travels across the space between you. You believe that what is happening in a laboratory in London cannot be instantly dictated by the configuration of atoms in the Andromeda galaxy. Feynman's path integral says otherwise. Because the calculation for a single electron's movement requires us to some histories that venture into the deepest reaches of space. It means the entire universe is participating in every local event. The electron hitting the screen isn't just a local interaction, it is a global negotiation. The outcome is technically dependent on the state of every gravitational field and every stray photon across the cosmos. Because those factors change the phases of the paths that pass through them. This implies that the universe is not a collection of isolated parts, it is a single, seamless, non-local fabric. We like to think of space as a container, a vast, empty room where things happen. But in the path integral view, space is more like a medium for these infinite histories to overlap. The here where you are sitting is connected to the there of a distant quasar, not by a long bridge-like signal, but by the fact that the history of every atom in your body includes a path that has touched that quasar. You are the product of a universal interference pattern. This is the disturbing depth Feynman found. It suggests that our isolation is a sensory limitation. We feel separate because our brains are only tuned to the winning paths, the ones that sum up to a coherent, local story. We are blind to the infinite, ghostly web of connections that link every point in spacetime to every other point. You aren't just an observer in the universe. You are a focal point where the entire universe is constantly interfering with itself to create the sensation of a single, local moment. We are left with a reality that is far more fragile than we care to admit. We began with the Double Slit Experiment, thinking it was a puzzle about light and matter. We ended with the realization that the very concept of a thing is a secondary effect. In Feynman's universe, the fundamental unit of reality isn't the particle, and it isn't the wave. It is the history. Reality is not a collection of objects sitting in space. It is a sum of everything that could have happened but didn't. When you look at your hands, you are seeing the result of an infinite cosmic census. You are seeing the one version of you that survived the violent mathematical cancellation of a trillion other versions. Those other versions, the ones where your atoms wandered to the moon or drifted back to the Big Bang, are not fake. They are mathematically necessary. Without them, the interference would be different. You would be different. This is the philosophical weight of Feynman's insight. We live in the stationary world. The world where the phases align and the noise goes quiet. We enjoy the luxury of believing in straight lines, solid walls, and predictable tomorrows. But beneath that surface of calm, the universe is a frantic, shimmering storm of every possibility occurring at once. We are like people standing on a single, narrow beam of light in a pitch-black cathedral of infinite size. We think the beam is all there is. We think the beam is the floor, but the beam is only there because the darkness around it is so vast and so chaotic that it forced the light to huddle together in a single, coherent line. You are not a traveler on a path. You are the intersection of every path. You are the silence that remains when the universe finishes its calculation, and as the electron strikes the screen, and the pattern forms, and the experiment ends, the infinite ghosts retreat back into the mouth, leaving us with the haunting suspicion that we are only ever seeing the smallest, most convenient part of what is actually there.